All right, so this is the lesson that we would have done yesterday. I want to make sure that we get this information because I don't want to spend any time next week doing a full lesson. We're just going to work on practicing continuity, infinite limits, and then reviewing for our test, which will be on Wednesday. So what we're being asked to do is to evaluate each of these expressions. There are 4 limits here and then an expression we need to evaluate based on the function f of x. And in order to do that, we should see a graph of the function. Now, the point of this here is going to be to illustrate why it is that limits are nicer, because in the past, we've had to, in order to graph a function like this, we've had to find the vertical asymptote, and then to find any horizontal asymptotes, we've needed to find the inverse of this function. So what we can say is that from looking at this equation, because we see that x minus 4 is the denominator, I know there's going to have to be a vertical asymptote at x equals 4, right? So I can start with that. I know that's there. But if I want to know where the horizontal asymptote is, what we've had to do in the past is say, let's find the inverse of this function. And so the inverse could be represented like this. Then we need to solve for y, and I'll just go ahead and pause and do that. So now I have my inverse function, and what I know about my inverse function is that it has a vertical asymptote at 1, so that means that f of x must have a horizontal asymptote at 1. And that gives me a lot of the information that I need in order to graph this thing. So then if I want a few points, I could plug in 5. F of 5 is going to be 7 over 1, so f of 5 is 7, and I could plug in 6. So that's going to be 8 over 2, that's 4. Plug in 7, that's 9 over 3, that's 3. All right, so that gives us a pretty good idea of what our function's doing on this side. And then we've got something similar going on the other side. So I could take that point, 6, 4, and that would be like this point here. And I'd have another point here. And so this is what the left side of that graph looks like. Okay. So that's what we used to have to do to graph these functions. Now with limits, we can help ourselves out quite a bit. We don't need to find the inverse function if I want to figure out what my function is doing as x approaches infinity or as x approaches negative infinity. But now that I have the graph here, I can evaluate each of these limits. So as x approaches 4 from the left, it looks like my function is approaching negative infinity. As x approaches 4 from the right, my function is approaching positive infinity. As x approaches infinity, my function is approaching 1. That's what's going on out here. X is approaching infinity. And as x approaches negative infinity, my function is also approaching 1. And f of negative 2 is 0. So I had to use old methods to graph this function. Now I could have evaluated each of these limits using what we know about evaluating infinite limits as well. But we can also graph this function now by just finding that vertical asymptote, which I'll do without doing all of this. So I don't need any of this. What I could do instead is I could just find the limit as x approaches infinity of x plus 2 over x minus 4. And that's just going to be the same thing as the limit as x approaches infinity of x over x, which is the limit as x approaches infinity of 1. So that's how I would know my function is approaching 1 in that direction. And in this case, it doesn't make any difference if I take the limit as x approaches negative infinity or positive infinity. It's still just going to be 1. So I could have known where that horizontal asymptote was using limits. And moving forward, that's what we'll do. So what we're going to do here is just kind of define continuity, which I think we defined in the last video, and then look at a few graphs and decide, is this an example of a function that is continuous at x equals c or not continuous? And if it's not continuous, then what sort of discontinuity are we dealing with? So remember, a function is continuous if all three of these criteria are met. So if f is defined at C, so let's check for that first. In A, is f defined at C? Yes, there is a point at f of C. So the first function checks the first box. In the second function, there is a point or a value for f of C, so that checks out there. Now for this third function in example C, there is no value at C. So this does not check the first box. F is not defined at C. So already this is not continuous, and we're not going to have to think about that one anymore if we're trying to just identify the ones that are continuous. D is defined at C. E, again, like C, isn't defined. There is no value at f of C, and F is defined at C. So then we need to take a look at the second criteria. Is the limit as x approaches C from the left equal to the value of f of C? And is the value of the limit as x approaches C from the right equal to the value of f of C? Now, sometimes you'll see these distilled into two different statements, one being, does the limit as x approaches C of the function exist? And then 3, is that value of that limit equal to the value of the function evaluated at C? So we may see them written that way as well. So we'll take a look at A. A, I would say that the limit, the left-hand limit and the right-hand limit are equal to the value of f of C. So those values exist and are equal, so A is continuous. For B, the left-hand limit agrees with the right-hand limit. So the limit does exist, but it doesn't have the same value as f of C does. So while the limit exists, the limit is not equal to the value of the function. So this is not continuous. And what we have here is a removable discontinuity. When we've got a hole in our function, that's a removable discontinuity. There's also a jump here. So this is like a jump and removable discontinuity, but we could remove that if we knew the equation of that function. Again, with C, this is also removable. But it is true that the limit exists. It's just that the limit is not equal to the value of the function at C, because there is no value of the function at C. For D, those limits don't agree. The left-hand limit does not agree with the right-hand limit, and neither of those agrees with the value of the function. So that's discontinuous. That would be a jump discontinuity. Right here, we've got another jump discontinuity. Because the left and right-hand limits do not agree, and they certainly are not equal to the value of the function at C, because there is no value of the function at C. And then we have the limits not agreeing. Although the left-hand limit does agree with the value of the function, this is not continuous either. It's another jump discontinuity. So we want to make sure that we understand when a function is continuous and when it's not, and that really is just boiling down to this checklist.